Hello everyone. Today I want to talk about Ling Auto, an interface between Ling and automated theorem provers. So first of all, I want you to have a general idea of what Ling Auto does. This will be the first three sections. Then we'll talk about into more detail about how Ling Auto works. And finally, we will talk about issues and future plan. So generally speaking, Ling Auto is a project that aims at providing proof automation for Ling. It will invoke automated theorem provers to solve goals in Ling. Let's say we want to prove the snake lemma. So snake lemma is a result in category theory. So we have this commutative diagram. And for example, this square means F composed with B is equal to A composed with F prime. So the details are not important. You just need to get a general idea of what's this problem. So first of all, we declare all the variables. In this case, there are just too many variables, so it makes sense to declare them before the theorem. The snake lemma can be divided into two parts, and suppose we want to prove the first part. This is what your proof will look like if you want to prove it manually. And this is what the proof will look like if you use Ling Auto. Note that you still need to supply all the required facts to Ling Auto. So this is an issue, and we'll talk about that later. Let's look at a simpler example. So this example is about the image of sets under functions and intersection of sets. So this equality can also be divided into two parts. The first part being the left-hand side is a subset of the right-hand side. And this is what we'll get if you want to prove it manually. And this is what we'll get if you use Ling Auto. Here is another example that involves real numbers. So in this case, you can see that Ling Auto can also reduce the proof length. Okay, so the above three examples are the type of problems that you will encounter in the math lab. However, Ling Auto is also potentially useful for software verification. So in software verification, you usually deal with integers, strings, bit vectors, float point numbers. So Ling Auto is expected to solve these types of problems. Okay, so what is Ling Auto? We know that there are two types of theorem provers: interactive theorem provers or ITPs, and automated theorem provers or ATPs. So for ITPs, the user completes the proof with the help of internal automation. For ATPs, the user only needs to specify the problem, and the prover will try to complete the proof automatically. However, different ATPs and ITPs are based on different logical systems. So for example, Ling is based on dependent type theory. However, most existing theorem provers, most existing ATPs are based on higher order logic and first order logic. So we need an interface between ITP and ATPs. We need to translate between the ITP's logical system and the ATP's logical systems. So in the case of Ling Auto, it translates between Ling and it translates from Ling to higher order logic and first order logic. So the translation is twofold. So first of all, you need to translate the problem from Ling to the target logical system. And after the prover has completed the proof, you need to translate the proof back into link. Of course, link auto is not the first interface between ITP and ATPs. We have existing interfaces like Isabella sledgehammer and cockhammer. So they do the same thing. Okay, so now that we've known what link auto does, let's talk about the limitations of link auto. So first of all, I want to mention the logical systems, the different logical systems that we will be talking about. So for first order logic, functions cannot take function as arguments, and quantifiers cannot quantify over functions. For higher order logic, functions can take function as arguments, and quantifiers can also quantify over functions. If we add polymorphism, then functions can also take type as arguments. So for example, on the right hand side, function.comp takes alpha, beta, and gamma as argument. And the theorem function.comp apply quantifies over alpha, beta, and gamma. To make it more expressive, we can also allow types to take types and terms as arguments. Okay, so now we get to the calculus of constructions. So for example, list takes a type as argument, and vector takes a type and a term. So this net is a term as arguments. If we add inductive types to calculus of constructions, we get calculus of inductive constructions. And finally, if we add other features like universe levels, induction recursion, proof irrelevance, quotient, type classes, we get real-life ITPs like Coq, Ling, and Agda. So what link auto does is that it translates from link to first order logic and monomorphic higher order logic. So if the problem is already in higher order logic, of course, link auto can deal with it correctly. If we add polymorphism and type classes to higher order logic, we get a bigger class of problems. And we find out that many mathlib problems will fall into this class. So for this type of problems, link auto usually handles them correctly. For dependently typed problems, the situation is a bit more complicated. So for universally quantified type indexes, sometimes link auto can find the correct instantiations. However, link auto does not deal with existentially quantified type indexes. So to be more precise, link auto is expected to correctly handle essentially higher order problems. And we'll get to this in the next section. So how about inductive types? Currently, link auto only has support for certain classes of inductive types, and only when SMT solvers are used as the backend prover. So, for example, here we have an inductive type called net, which is essentially the type the set of natural numbers. So it's easy to prove that if x is not equal to 0 if and only if x is the successor of some net. So let's see whether link auto is able to recognize this property automatically. So in the first example, the hypothesis is x not equal to 0, and the goal is X is the successor of some net. We can see that Ling Auto can solve this. This is because we are using SMT solvers here. However, if we turn off the SMT solver and use duper instead, Ling Auto cannot solve this problem. However, this does not mean that Ling Auto fails because of inductive types. It's just that Ling Auto will not automatically recognize properties of inductive types, and users can explicitly supply these properties to Ling Auto as a workaround for this limitation. So for example, if you supply the property of this inductive type, which is expressed by net.cases, then Ling Auto is able to solve the problem. Okay, now let's get into the detail of how Ling Auto works. So first of all, we will focus on an example about list append and list map. So basically, we want to prove that AS append BS append CS mapped by F is equal to AS mapped by F append BS mapped by F append CS mapped by F. So we can see that we need the associativity of append and the distributivity of map over append. So to highlight polymorphism, we will display all the implicit arguments. So we can see that there are three polymorphic functions, namely EQ, map, and append. And they occur both in the hypothesis and in the goal. So how do we get rid of this polymorphism? First of all, let's focus on the goal. For the goal, it's actually very simple. So we notice that although map is polymorphic, map applied to A and B as a whole is monomorphic. So it behaves just like a monomorphic function. And the same holds for append and EQ. So we can apply this translation, and the goal will be turned into a monomorphic one. So what about the hypothesis? Of course, we want to apply the same technique to the hypothesis. However, we notice that the type quantifiers in the hypothesis, so the types are quantified in the hypothesis. So for example, the type argument of append is alpha, and alpha is quantified. So we need to instantiate these quantifiers first. But how do we instantiate these type quantifiers? So let's take a look at how the quantifiers would be instantiated if we were to prove it manually. So there are many ways to prove this property, and here I've shown two ways. So you can see that the type argument of map append is always A and B, and the type argument of append assoc can be A or B. So let's try to come up with an algorithm of instantiating the type quantifiers. So we can see that, for example, if the type argument of append assoc is instantiated to be A, which means alpha becomes A, then append alpha will become append A, which makes it the same as the append A inside the goal. And the same holds for append assoc B and map append AB. So you get the idea. For each polymorphic function f and for each hypothesis, the quantifier of the hypothesis, is instantiated such that there exists an occurrence of f in the instantiated hypothesis and an occurrence of f in the goal with the same type arguments. Okay, now that we've seen an example, we can talk about the monomorphization procedure as a whole. So in the monomorphization procedure, we maintain two sets, which is lemma insts and const insts. For lemma insts, it consists of lemmas or lemmas with type arguments partially instantiated. So for example, map append A, map append AB, and append assoc A will qualify for lemma insts. So in the beginning, we apply proof by contradiction, which means that we introduce the negation of the goal into the context and replace the goal with false. So now, the local context consists of the negation of the goal and the original hypothesis. And this will be the initial state of lemma insts. Okay. And const insts consists of instances of polymorphic functions, like map AB and append A. And we want to collect const insts from lemma insts. To qualify for const insts, all the type or dependent arguments of the polymorphic function must be present, and quantified variables does not occur in the type or dependent arguments of the function. So for example, this append alpha will not qualify because the type argument alpha is a quantified variable. However, this map AB will qualify because both arguments are present and does not contain quantified variables. So the initial state of const insts will be collect const insts applied to the initial state of lemma insts. Okay, so in the process, we will repeatedly match lemma insts with const insts. So it's the same as the previous example. So we want to determine how the quantifiers will be instantiated. So we just match the type argument of the same polymorphic function. And in this process, we will generate new lemma insts. And we will collect new const insts from these new lemma insts. So this process may loop forever. So we have to set a limit for the number of cycles. Okay, so in the end, we want to collect all the eligible lemma insts. And a lemma inst I is eligible if and only if all the polymorphic functions in F basically qualifies for const insts. So the criteria is the same. Okay, so let's take a look at another example. So this example is actually the same as before, except that we are using type classes to represent append here. So you can see that this plus plus is actually pretty complicated. It's happend.happend list alpha list alpha list alpha inst happend, and this inst happend can also be expanded. So how do we deal with the type classes? It turns out that it's the same as before. So yes, happend.happend is polymorphic. However, after the first three arguments are supplied, so for example, happend.happend list alpha list alpha list alpha becomes monomorphic. However, ling auto does more than this. So ling auto also requires that the type class instance argument is present. This is because we want to do type class inference before monomorphization. So it turns out that this is easier to implement. Okay, so let's take a look at the snake lemma again. So in the snake lemma, we see a hypothesis called ing-L, which says the up arrow L is injective. So what is this up arrow? It turns out that this up arrow is actually pretty complicated. So you can trace back, so you can hover over this up arrow L and you will see that it's actually funlike.core, and you can trace back the type classes. And if we use set option pp.r true, we will see that ing-L is actually this stuff. This causes problems for LingAuto because all the functions, for example, funlike.core, add monoid home, and add monoid.to add 0 class, all these functions are polymorphic, and they will be collected to become constants, and they will enter the matching procedure. This will generate a lot of useless output. So this will make the monomorphization procedure generate a lot of useless output. So in LingAuto, to deal with this problem, the match procedure will ignore type class instances. Okay, let's look at another problem with the snake lemma. So here in this square zero hypothesis, you can see that there is a quantified variable a, and a occurs as the last argument of funlike.core. So this is the signature of funlike.core, and we can see that the last argument is a dependent argument because the return type depends on it. So according to our criterion, this quantifier must be instantiated. But is this really true? Actually, it's not, because if we supply the first 4 arguments to funlike.core, we will find out that the return type no longer depends on the last argument. And why? This is because beta is instantiated with funx to beta 0. So the return type beta a is equal to funx to b0a is equal to b0. So this funx to b0 is a constant function, so its output does not depend on its input. And so the return type no longer depends on the last argument. In this case, if we consider the last argument to be a dependent argument, then the monomorphization procedure will instantiate this quantifier, and its output will be insufficient for proving the result. So in LingAuto, whenever it wants to determine whether an argument is a dependent argument, it will look at how previous arguments are instantiated. Okay, so of course there are other things we need to consider during monomorphization, such as inductive types and definitional equality. And for proof reconstruction, it is significantly more technical than monomorphization, so we will not talk about it. Okay, so finally let's talk about issues and future plan. So LingAuto is still under development, which means that it has bugs and may lack important features. So in the previous snake lemma example, we saw that we need to supply a lot of facts to auto. So all of these facts are used in the proof. So this is problematic because the user might not be able to remember all the names of the theorems. And so if a premise selection component is implemented, it will look at all the existing theorems and pick out the relevant ones. So the user will no longer need to supply all the facts manually. We also want LingAuto to automatically recognize definitional equalities of match expressions. So for example, here we have an inductive type that has only two elements, and we defined a match expression over this inductive type. So this match expression has definitional equalities, which is just the function applied to z1 is equal to 10,000, and the function applied to z2 is equal to 5,000. So you can see that LingAuto is not able to recognize the property automatically. So if x is of type zone, then x dot mean area 1. Of course, it's bigger than 5,000, but auto is not able to recognize this property. However, again, you can supply this property explicitly to LingAuto, and it will solve this problem. So another missing component in LingAuto is the higher order logic to first order logic translation. So currently, we already have a translation from Ling to monomorphic higher order logic. However, we don't have a component from higher order logic to first order logic. And we know that SMT solvers are based on FOL. So if the problem is already first order logic after monomorphization, then LingAuto can send it to SMT solvers. However, if it is not in FOL, LingAuto will fail. And finally, we also want proof reconstructions for SMT solvers. So currently, LingAuto uses sorry when the SMT solver returns a proof. And after we implemented proof reconstruction, this sorry is no longer needed. Okay, so that's all. So if you have any questions about LingAuto, you can ask it on Zulip, and pull requests and issues are also welcome.